Okay, so the screen is shared, right? You're able to see the screen? Yes? No? Yes? Okay, cool. So what we'll do today is this notion of duality, and in particular what's called Lagrangian duality for constrained optimization problems. Okay, so you already saw a notion of dual in the context of linear programs. Right. So this is something which is more general for any constrained optimization problem. Uh, the dual is another related problem, and we'll see the different notions of dual. So one is Lagrangian duality, then there's something called Wolf duality, then there's something called Fenchel duality, and so on. Okay, so we'll only look at the Lagrangian duality, which is written in terms of the Lagrangian function, which you already saw. Okay, so the primal problem that we are considering is of this form, right? So you're trying to minimize some function subject to some constraints. Gix is less than or equal to 0, some inequalities, some equalities, and you have that x is in some capital X. Okay, so you can think of this capital X as the domain. So in all the problems we saw, like when we wrote the Kkt conditions and all that, this X was just Rn. Okay, so X and Rn. But in general, what you can do is you can think of X. I mean, there's some flexibility in writing this X in capital X. So one thing is, of course, I mean, you can use it to handle some of the constraints in a different manner. So we will see some examples of this. Okay, so the examples we saw so far was when the set X was Rn. Now you could also have the set of integer points, okay, X as an integer set, and even for those problems you could write the dual. Okay, so that's a subtle difference that we had from the Kkt conditions. So the Kkt conditions that we wrote, those were all for the space of continuous problems. Okay, but this dual is something a little more general. You can write it for any constraint problem. Okay, so that's why I differentiate from this. Now another possibility is, the set X. Like I said, you can handle some constraints differently. So something like if you have xi is greater than or equal to 0. So if you want, you can, if you don't want to treat it separately, you don't want to look at it as in like what you would do for the inequality constraints, if you don't want to treat them along with that, so you can, so that's why you have this X written separately. Okay. Yeah, so these things will get a little more clear later when we do some examples, but for now you can think of this as the domain. Okay, X is just the domain of on which you're defining this problem. Okay, so so the dual, as I said, it's a related problem, and if you remember from our discussion in linear programs, what you did was for a minimization problem, you always tried to find a lower bound. Okay, and the idea was to find the best possible lower bound. Okay, and the same idea holds even here for general constraint problems. You're trying to find a lower bound to the primal problem. Okay, and the tool that we have here is now the Lagrangian function. So we've seen the Lagrangian when we defined, when we tried to solve constrained optimization problems, and that is a tool that you will see it will help us to find a lower bound for the primal problem. Okay, so again, the problem is this. I'm just writing it again, min fx, such that these are the inequalities and you have equalities. And this is a domain. And I'm calling this entire set of x, which satisfy all these. So out of the domain, out of this x, out of all the points in this capital X, the ones which satisfy these constraints, that I'm calling it as omega. So omega is the overall feasible region for this optimization problem. Okay. Now, if I have to write the Lagrangian here, right? So what I would do is, from our discussions earlier, like we'll just have just a multiplier for each of these constraints, and then I will write the Lagrangian written in this way. So for any x, lambda and mu, the Lagrangian is just written in this manner: fx plus summation I equals 1 to m lambda I gi of x plus summation j mu j at jx. Right, so this is what we saw as the Lagrangian. Right now, for if you take any x in omega, so one thing was we were also interested in the lambdas which are greater than or equal to 0 when we wrote the Kkt conditions. So assume that here also we have the lambdas as greater than or equal to 0. Now for any x which is feasible, for x in omega, so in this I'm looking at all x which satisfy these constraints and they belong to this domain. What can I say about this term? What do we know about this? Okay, am I audible?
Yes, ma'am.
Okay, so what do we know about this term, this lambda I
It
gix?
is 0.
Yeah, so that is only at the optimum, like when it satisfies a Kkt point, the complementary slackness.
Then
But
it
here
is
I'm
negative.
it's less than 0, right? So here the lambdas are just anything which is greater than or equal to 0. And for any feasible point, I have that this holds because gix is less than or equal to 0 for all x in omega. And lambda is positive, so this term is less than or equal to 0. Now, what about this term? What do we know about this for any feasible x?
0.
This is equal to 0, right? So
Yes, ma'am.
what we have is this Lagrangian function. So this L, so any x in omega you take, L of x lambda mu. So for, of course, lambdas have to be greater than or equal to 0. So for all these lambdas which are greater than 0 and for any x you take in omega, this L x lambda mu is going to be less than or equal to f of x, right? Because f of x minus something is going to come. So that is going to be less than or equal to f of x. Okay, and again, this is true for all x in omega. So now if you want a lower bound, right? So if you take a lower bound over this, so if you take inf of x in omega, L x lambda mu, so what happens? It will still be less than or equal to f of x, right? So this is also true for every x in omega. So here you are allowing x to vary, and in this side you're taking the minimum value of the Lagrangian for a fixed lambda. Okay, so then this is going to be a lower bound to f of x, and in particular this is going to be less than or equal to fx star, or let me call this value as p star. So let this objective be p star. Okay, the best value. So this is going to be less than or equal to p star. Okay. Now, so this is an infimum over x and omega. Now, remember, omega is a subset of your domain, right? So you have your original space. The domain is something like this, some x. Okay, set of all points here is x. Now, omega is some subset of this. Okay, so if you take, so instead of saying x in omega, now if I say, if I take the infimum over x in capital X. Okay, so instead of omega, I'm going to say that it's x in capital X. So what can I say about the relation between this term and this term?
We will achieve optimum at the same time.
So you mean to say these are going to be equal? Um,
Not sure.
Rohit?
Not sure.
Okay, so what is going to happen here is like, so this is a function and the lambda and mu are fixed. So lambda is greater than 0, mu is also fixed. And you're trying to find a minimum over x and omega. Now, on the other hand, you're taking a larger set, capital X, and if you're trying to find the minimum, so the minimum over the larger set is always going to be less than or equal to the minimum computed over a smaller set. Do you agree?
Yes, ma'am.
That's true, right? I mean, a larger set means you have more options. So there is a possibility you'll do even better in terms of the minimum. Okay, so this relation also holds true. Okay. So the reason why we would go for something like this inf of x in smaller, I mean, in this capital X, this larger set, is because sometimes this problem may be easier to solve if your X is just the domain, and it could be an unconstrained problem. Okay, so we will use this as the lower bound. Okay, and we'll define what is called the dual function, which is just this quantity, the infimum of this Lagrangian over all x in this capital X. Okay, so this is always going to be less than or equal to f of x for every x in omega. Okay, so this is always a lower bound. Okay, now what, yeah, I hope up to here is it okay? Are there any questions on this? Do you understand why this is a lower bound? Anything you want to clarify? You can
Yes.
type or you can ask. It's clear, Rohit. Okay, what about the others? It's clear? Okay, it's clear, fine. All right, so now given this is the dual function, so this is going to be a component of the overall dual that we write. Okay, so this is a lower bound. Now, what is the best you can do? Okay, so the dual problem is going to be what is the largest value of this dual function. So remember when we wrote this dual function, we said that a lambda and mu, these were fixed. So this one assumes that the lambda and mu are fixed. Okay, so now any lambda you take, this is going to be, this is a lower bound. This theta of lambda mu is a lower bound. Okay, so how best can you do? How far can you go? And that is what the dual problem is. Okay, so what is the maximum value of theta of lambda and mu if you're allowed to vary the lambda and mu? So now for this problem, the decision variables are lambda and mu, where lambda is all greater than or equal to 0 and mu is unrestricted. Okay, so if I have to write this fully, so this would be maximum, again, lambda is greater than 0, all the component wise they're greater than 0 and mu unrestricted. And this theta of lambda mu is, again, it's an inf problem. So it's an inf over all x in capital X, f of x. So that's just the Lagrangian plus lambda I g I x plus summation mu j h j x. Okay, so it's actually a two-stage problem where for a fixed lambda you find this inf problem, and then you find the best lambda which maximizes this inf problem. Okay, it's a two-stage problem, right? Of course, for this reason, these lambda and mu, these are called the dual variables because those are the variables for the dual problem, and they're also called Lagrangian multipliers. This we already saw when we did Kkt conditions. Okay, so one thing that, of course, the way it is defined, you'll have that this theta of lambda mu is always less than or equal to p star, and the value of this dual problem, let's call it d star. Okay, and so d star is always going to be less than or equal to p star. Okay, it's just the consequence of the way we have defined it. And in general, so in the case of linear programs, what we saw was if the primal had a finite optimum, then there's no way but the dual had to have a finite optimum. Okay, but this is not true in general. You will have the d star is less than or equal to p star, but it could be that even the primal has a nice structure and it's optimum, but the dual can, the dual may be, unbounded, or it might not have a feasible point. All those things can happen. Okay, so it's no longer, there is no structural assumptions that we're making, so all these things can go wrong, but only thing that is guaranteed is that the dual optimum is going to be less than or equal to the primal optimum. Okay, yeah, so there are, under some special conditions like convexity and with some more assumptions, these two optimum values will be equal, and we'll also see that later on in the class. Okay, but in general, you always only have that d star is less than or equal to p star. You never have that those will be equal. Okay, So yeah, so other is this clear? Like we will see some examples of how to write the dual in some time. But I hope like this two-stage problem, it's clear, right? I mean, what we're trying to do. I'll also just give you a geometric interpretation of this before we move on to some examples of this. Okay, so let me just take the case where you have one constraint. So suppose I'm considering a problem like this: minimize fx subject to g of x is less than or equal to 0. So I have just one constraint, and x is all of Rn. So x in x, and let's say that is just Rn. Okay, so yeah, so this is the problem. And in terms of the Lagrangian here, so there's just one constraint. So let me call this multiplier as lambda. So L of x lambda is just f of x plus lambda g of x, right? Okay, and the dual problem here is, so theta of lambda is inf over here. So inf of x in capital X, f of x plus lambda g of x. Okay, so I'm just going to try to look at it from the viewpoint of a different space. Okay, so what I'm going to do is I'm going to take every point x in capital X, and I have these two numbers f of x and g of x corresponding to that. Okay, so I'm just going to write a new space. So G, it's a new set. It consists of all. There are 2 points here. I mean, those will correspond to the f of x and g of x, and I will say, like, let me call these values g of x as z1, and let me call z2 as the f of x. Okay, and this going to do for every x, for every point in the domain. I'm going to collect these g of x and f of x, and I'm going to form a new two-dimensional set like this. Okay, so this g is in R2. It's a subset of R2. Okay, so it's just for visualization purposes I'm doing this. So what happens is, this is the primal problem. Okay, and the primal problem in terms of this space, it's just going to be minimize. So f corresponds to this z2, right? So it's just going to be minimize z2 such that the g of x values, so that corresponds to z1 is less than or equal to 0, and I have z1 z2 lying in g. Okay, so the primal problem is just again this. Okay, um, right? And in terms of the dual, so if I write for a fixed value of this theta lambda, so let me just write it in a different color. So theta lambda, so what would this boil down to? So again, f of x is just z2, right? So it'll be some inf will be there, but this value will be z2 plus lambda z1 over all z1, z2 in G. Okay, I'm just writing it in terms of a different space. Um, does this make sense, or do you want me to just pause and, so that it sinks in?
Understood, ma'am.
Understood? Okay. What about the others? Is this clear? Bhavna? Yes? Okay. Okay, so okay, fine. So I gather that this is clear to you all. So the reason why I'm doing this, writing it in a different space, is just to see some geometric interpretation for the dual. And actually, the dual problem is you're trying to maximize theta of lambda. So maximize this inf of z2 plus lambda z1, okay, over z1, z2 in G. Okay, and yeah, this was exactly theta of lambda. I'm trying to maximize it over all lambda greater than or equal to 0. Okay, so we'll now just look at this problem. So this is the primal, and this is the same dual. Okay, so let me just try to draw an illustration for this. So this region, let's just look at the primal now. So we are looking at the space of Z1s and Z2s, okay? And there's some set like this, Z1, Z2 in G, so maybe something of this form, okay? Let me just draw it a little nicely. Okay, so something like this. Okay, so this is the set G. Okay, now in terms of the primal feasibility, so you're interested in all the Z1s which are less than or equal to 0. So that would just be this region. Okay, so this is the region of interest for the primal. And if you look at, the optimal value, so you're trying to minimize Z2 subject to this Z1, Z2 in this region, which is shaded in blue. Okay, so from here, the optimum is going to be this point. So the point with the minimum value on the Z2 axis. Okay, so this is going to be the primal optimum. Okay, so now let's look at what the dual is going to do here. So in particular, let me just focus on this theta of lambda. We will come to this maximization problem later, but just let's focus on theta of lambda. And let us just look at for a fixed value. So suppose we are given a lambda, and let's just try to understand this objective. Suppose I say that, I'm looking at all points, say Z2 plus lambda Z1. So let's just call it lambda 1, okay? Z2 plus lambda 1 Z1 is some value, say C1. Okay, so this is the set of all points Z1 and Z2 such that their objective Z2 plus lambda 1 Z1 is equal to C1. So this is not necessarily theta lambda because it need not necessarily minimize this, but I'm just trying to understand what this region is. Okay, so now if you look at this equation, so the set of all Z1 and Z2 which satisfies this is just the line, right? It's just the line. And so in particular, this is a line with slope minus lambda 1, okay? And it has an intercept of C1. So maybe something like this. Okay, so the set of all Z1, Z2s, that can be in G or outside G, whatever, I don't care. But this is going to be the line Z2 plus lambda 1 Z1 equal to C1. Okay, and I drew it in this manner with a negative slope, right? Because this is going to be a negative value. Lambda 1 is, we are interested in lambda 1s. Ultimately, the lambda 1s will be all positive. So this negative, so this line will have a negative slope, and that's why it looks like this. Okay, so now this point here that we are having, this intercept is equal to C1. Okay, so for a fixed value of lambda, if I'm trying to minimize this Z2 plus lambda Z1, so now we are coming into the dual function, this theta of lambda. So what does it mean to say that I'm trying to minimize this value? So I'm trying to find, this won't be C1. I mean, I'm trying to look at all lines with this slope, the slope of minus lambda 1. And I'm trying to see which is the one which has the least intercept. So because C1 is the intercept, and so this objective is looking at the minimum value of intercept out of all the lines which go through G. Okay, so if I look at, let's look at another line with the same slope. So something like this. So this will have a larger intercept. Now something here will have a smaller intercept. So the intercept is something here. Okay, and how far can this go on? Okay, so yeah, so how far can this go? How far, I mean, how much lower can I bring it? And that would be given by something like this, right? So some point here, if I take, this is going to be the lowest intercept I can get. If I take some other point now here, some other line, which is again parallel, I'll get an even lower intercept. But the thing is, that is not the infimum. So out of all the lines which pass through this set G, which is the smallest intercept that I can get out of all lines with the slope of minus lambda 1. Okay, so this is going to be the best value. So this is going to be theta of lambda 1. Okay. I'll just pause for a minute. Everybody is very quiet. So is this clear? Is there something that's bothering, or anything you want me to explain again?
Ma'am, here we were varying lambda, keeping what like for a given lambda one we are saying, or we are varying lambda one.
So whatever I said right now is for a given lambda. So I'm not looking at the dual right now. I'm just looking at this theta lambda. Okay, so where lambda is fixed, and I'm just trying to solve this problem. I'm trying to find the infimum of this for a fixed lambda. Okay.
Yes,
So
ma'am.
that,
Yes, ma'am.
yeah, yeah. So yeah, so this is so when you say theta of lambda 1, it means that the lambda is fixed. You're not going to play with the lambda. You're not going to change that. Now, this is the theta of lambda. And what I'm interested in, once I have this theta of lambda, I'm trying to find now the lambda which will maximize this intercept, this lowest intercept that has to get maximized. So I'm trying to find the values of lambda so that this intercept can move even higher. Okay, so all this theta of lambda is now a lower bound for the primal optimal. P star is here and theta of lambda 1 is here. Now, if I took, some other slope, okay, let me, don't know. Okay, fine. Let me just try to draw maybe some other slope. So suppose I took lambda as something like this, a slope of this form. Okay, so this probably will give me a better value, better lower bound, right? So if I look at the intercepts, so this one, if I take, so let me call this as z2 plus lambda 2z1. So I'm taking another lambda value, and this is something, say, let me say this is d1. Okay, so this is another intercept I'm getting. So this is another value. Now, if I take all possible lines with the slope lambda 2, and then I look at the one with, the ones which pass through the set G, and then I look at the one with the lowest intercept, then what I'll get is something like this, right? Maybe something of this form. Okay. Something like this, parallel to this blue line, but maybe this is the new lambda I get. Okay, I mean, this is the new intercept I get. So this will be something like theta of lambda 2. Okay, so this was better than theta of lambda 1. So like that, how much can I go? Okay, how can I bring it even higher and higher? Okay, this worst intercept, the lowest value of intercept, how can I improve it? So in this case, it would be something like, maybe something like this form. Okay, something like this. If you take, that is perhaps the best that you could get. Okay, so in this case, so that is what is the dual value. So this would be the D star that I get. Okay, so it will not be equal to P star, but there'll be some gap here. Okay, so that's what the dual is doing. Now, I don't know, why didn't we look at, let's say, a line like this, something of this form? So, or maybe if you looked at, a line like this, maybe you could have done better. The drawing is bad, but why didn't we do that? So maybe okay, let me just draw another figure so that this is getting cluttered. So maybe something like this. Suppose the region is like this. Okay, and this is going to be the region of interest for the primal. So this is P star. And my claim is the dual, the best value you can get is something like this. So maybe this is going to be my T star. So that's my claim. So yeah, so why cannot it be like something like this? So if I do this way, maybe this is a better value, right? So why can't this be the D star? Right?
Lambda is greater than 0.
Yeah, exactly. So you need to look at all the lambdas which are greater than 0. So you're looking at only lines with a negative slope. Okay. So yeah, that's the whole idea. And one thing to note is when you are looking at the dual function, you're looking at this whole space Z1, Z2 in G. Okay, so yeah, it's not just this left hand side. You're looking at everything. I mean, all lines passing through this whole space. Okay, even through these points. Okay, so to see this, maybe you can see one more example. Maybe suppose you had something like this. Okay. Okay, so this would be the P star because I'm looking at everything which is less than 0. Now, in terms of the dual, I mean, it has to be a lower bound considering all the G's, right? This whole set G. So what I would look at is maybe I would say something like this, somewhere here. Okay. Oh, okay. Okay, my drawing is very bad. So something here, okay, like which, so that I mean that, this something passing through this part, this is the optimal. So the D star is somewhere here. Okay, but why don't I look at something? If I ignore this thing, I would get some line like this maybe, which is a better value. So that doesn't happen because in terms of the dual, you are looking at the minimum intercept among all lines which pass through this G, this whole set G, and not only this feasible region. Okay, so yeah, so that's the interpretation of the dual. From you're trying to get something with respect to the intercept, the best worst intercept in some sense. Okay, is this clear? You're all quiet, so I want to just hear from you whether it's fine or are there any questions.
Ma'am, why in the case of primal, the optimal should be on the Z2 axis?
So you mean this one? I mean, why it's the optimum is on Z2. So the thing is, we are looking at the value of Z2. Okay. So in particular, like the Z2 is the one in the objective, right? That is symbolic of f of x. Okay. So from all these points, which is the one with the lowest value of Z2? Okay. Yeah, you can have something like, yeah, I guess in these cases, even this, okay, the primal optimum would be,
Yes, ma'am. It wouldn't be the one on the axis actually.
it wouldn't be on the one on the axis. Let's see. So let me just draw it a little better. Okay, so for any point here, what would this be? So this would be some value. G of x takes a negative value and f of x takes some value here, right? But I think what is happening here is such a point is not in your domain, right? So for this okay, so let me just go over this one. So if you have something like this, so you're saying the primal will be this itself. This will be the P star. That's the claim you're saying, right? Bhavna, that's
Yes, ma'am. Yes, ma'am.
okay. So why? So the set. So in that case, the set G also. This should also have been part of the set G, right? So the thing is, the set G is only, this is outside the domain. A point like this is probably outside the domain. And so if it had to be, if you were interested in this, then it had to be, like the set G itself would have to be something like this, right?
Ma'am, why Z1 has to be 0? There's no constraint on Z1. It's Z1 less than 0, right?
Yes, Z1 less than 0. But also you have that you're also taking everything only in this domain X. So when you take that, the set of points which satisfy, I mean, when you take all the points in X and then you're looking at the G and F, then the set you're getting is this one. Okay. So a point like this where, oh, you're saying like it need not be here, so something else. So Why doesn't it come? So my sense is that this, otherwise, like how would this come as G, right? Otherwise, if this point you could consider as the one with the lowest f of x, then your G will also be something like this, right?
And why this is the case? Like this point on the left side of G, the minimum point is there in G, right? And so why this can't be the optimum? Because we want minimum value of Z2. So in that case, the minimum value of Z2 would be at the center.
Would be this one. I see. Let's see what you're saying. Okay. Okay, let me just think about this. I think this needs a bit more of thought. Somehow I've kind of missed this idea. Let me just think about this and get back to you about why this is the case. So yeah, so this is a good point actually. So I'll come back to you on this. Okay, on this interpretation. Yes, Siddharth.
Ma'am, D can lie anywhere in that part, that the left side of the region, left side of the y-axis of
So
the.
D. So you mean this D star?
No, ma'am, I was talking about the feasibility of D. So D can lie anywhere in the left part of the y-axis in that shaded region.
So you mean D can be something here?
Yeah, D can be anywhere. Like I'm asking, like if D can be something anywhere there, and if that point is lower than uh, sort of could see the contradiction, but like okay, I'll
No,
think.
so the thing is this theta of lambda when we take, so all this corresponds when you take z2 plus lambda z1. So that corresponds to intersects. This value, exact value of z2 plus lambda z1, that corresponds to the intersect, the exact value of it. Okay, so that's why we are only interested in the intersects. Now, any point you take on this line, for example, this line you take, yes, the Z2 plus lambda 1, Z1 for that will lie on this. I mean, it will exactly be equal to this value. Okay. But in terms of the inf value that you're taking here, the theta of lambda is exactly the value of the intercept. You could have some points Z1 and Z2 here, which will give rise to this value of intercept. That is fine. But in terms of the overall value of theta lambda, that is given by the intercept. Right, Siddharth?
Yes, ma'am, got it. Got it.
So when we draw this kind of a thing, right, D star, so there is this point here, right, in G, which is going to give you if you take the Z2 plus lambda Z1, you are going to get this D star. That is fine. But the value, to see where that value lies, you're looking at the intercepts. Okay. So I'll just, maybe get back to this part about what Bhavna asked, maybe in the next class, but let's maybe just do an example of how you can work out the dual so that, this idea of computing this max min kind of thing becomes clear. Okay, so I'll just take a problem like this, where you have, it's again in 2 dimensions. So min x1 square plus x2 square, and these are all linear constraints. Okay, so now what I'm going to do is, I have a hyperplane like this, minus x1 minus x2 plus 4 is less than or equal to 0, and x1 greater than 0 and x2 is greater than or equal to 0. So what I will do is I will consider these constraints, I will consider separately. Okay, so that I will call it as my set x. So x is an R2 such that x1 is greater than or equal to 0 and x2 is greater than or equal to 0. Okay. And yeah, so I'm going to write the Lagrangian, keeping in mind only this constraint. Okay, so the reason for this, you will see, it just simplifies the way in which the dual can be is written. So you can also take this as your set of constraints, and another option is to take x is just x in R2. So you will have 3 multipliers here. Okay, so that is also something you can do. But let's just see how this works out. So, I will leave it as an exercise for you to do the other part where you take all the constraints together. Okay, so there is one constraint as far as we are concerned, and that is it has a multiplier of lambda. So the Lagrangian here would be x1 square plus x2 square plus lambda times minus x1 minus x2 plus 4. Okay, so in terms of the dual function theta of lambda here is just the minimum in over x in this set. So x1 greater than or equal to 0, x2 greater than or equal to 0, and x1 square plus x2 square minus lambda x1 minus lambda x2 plus 4 lambda. Okay, so this is the dual that we are, the dual function. So this is the dual function. And this you want to minimize over x1 greater than or equal to 0 and x2 greater than or equal to 0. Okay, so if you look at this function now, the x1s and x2s can be like separated out. So this lambda is fixed. So this is just x1 square minus lambda x1. Then you have x2 square minus lambda x2 plus 4 lambda. Okay, and you're trying to minimize this over all x1s greater than or equal to 0 and x2 greater than or equal to 0. Okay, so there are two separate functions I can think of, which I need to minimize both. Okay, so if I try to minimize this function, so this is a convex function in x1. Okay, and the minimum will be achieved at x1 is, so if I just take the gradient, I'll get 2x1 minus lambda is 0, and this will give me x1 is lambda by 2, and similarly this will give me x2 is lambda by 2. And you can check that this is indeed, these are the minimizers of this function, because these are individually convex in x1 and x2, and they're separable, so you can just sum them up, it's going to be minimized. Now you're always going to consider the case where lambda is greater than or equal to 0 finally, right? When you maximize theta of lambda over lambda is greater than or equal to 0, that this is going to be there. So this x1 and x2, ultimately you're going to get positive values always. Okay, because lambda is greater than or equal to 0. So that's why this constraint you could just ignore it. Okay, so now let's just write theta of lambda. Okay, considering this x1, the optimum value of x1 is lambda by 2 and x2 is lambda by 2. So can you tell me the value? Just substitute it here in this function. So can someone tell me the values?
Lambda square by 4 minus lambda square by 2
Square
plus,
by 2. Yes.
Plus the same thing.
Yes, plus into 2. 2 times this. Plus 4
4
lambda, right? So this is equal to what? So
minus lambda square by 2. And by 2 is not needed because it will get cancelled out.
So this will give minus lambda square by 4 and into 2.
Right, by 4 into 2.
So this will be minus lambda square by 2 plus 4 lambda, right?
Yes.
So the dual, if you write the overall dual, this is just going to be maximize this quantity subject to lambda greater than or equal to 0. Okay, so this is the dual of the original problem. Now, if you solve this dual, so this is just in one dimensions, right? So it's going to be easy to solve this. So if you just ignore this lambda greater than or equal to 0 constraint, so what you're going to get is, if you treat it as an unconstrained problem and then see whether, the optimum for the unconstrained problem has lambda greater than or equal to 0. So that's the first approach we will do. Or you could also write Kkt conditions and all that, or you can visualize it. There are different ways to do this. So, but in short, what you're going to get is lambda. So if you take the gradient, you're going to get minus lambda plus 4 is 0, right? So lambda star is equal to 4. So that anyway satisfies lambda greater than or equal to 0. So the unconstrained minimum for this, unconstrained maximum for this problem satisfies these constraints. And of course, you have to take the second derivative. In this case, it's a concave function. So the second derivative will be less than 0. So indeed, this is the maximizer. Okay, so in terms of the objective, so the d star you get here is what? If you substitute this value of lambda, what do you get in the function? So this is d star.
Eight.
So how do you get that? So minus 8
Plus
plus
16.
16. So this is going to be 8. Okay. So now let's just see the primals. And this is a simple case where even the primal, you could possibly solve it graphically, or you could also apply the Kkt conditions we learned earlier. So when you apply the Kkt conditions, you have to have these multipliers for all these three inequalities, okay, not just one of them. So in this case, like if you look at it graphically, let's just see what happens. So what you're going to get is x1 plus minus x1 minus x2 plus 4 is 0. So the hyperplane corresponding to that is something like this. x1 is 4, x2 is 4. And the origin is not part of it. So you have this side. And you have x1 greater than or equal to 0, x2 greater than 0. So basically this whole region. Okay. And now the contours are x1 square plus x2 square. So that's the contours of the objective are like circles. So something like this. Okay. And you want this to be minimized. So you can see that, what minimizes is going to be something that touches the circle. Okay. Right? Because it has to be feasible. So all these, if you look at the feasible points, I mean, if you look at all the contours in terms of the feasible points, what you're going to get is something like this. All these are going to be valid objective contours. So the one which minimizes is something like this. Okay, so so it seems that this constraint will be active. Okay, x1 plus x2 will be equal to 4. And then what you can get, like in terms of, I mean, you will see, okay, if you can solve this, then you will get that the objective, the best value here is going to be x1 is x2 is 2. Okay, and in terms of p star, so the primal optimum, the maximum here is going to be 4 plus 4, which is again 8. Okay, and that matches with the dual. Okay, so it's just an exercise on how you can write the dual. So we'll see some more examples later, and yeah, I will also clarify this part about the interpretations, like why, for this kind of thing. Like, let's just go into a bit more depth about this. Okay, so yeah, so I think I will wrap up here for today. And I'll just hang back in case there's something you want to chat about. So thanks a lot for coming. We'll see you tomorrow afternoon.
Thank you, ma'am.